There is a perception that rad-hard components are too expensive to use in CubeSats. The reality is that you can reduce the project risk significantly at a relatively tiny cost compared to the overall project budget. VORAGO Technologies, a privately held fabless semiconductor company based in Austin, have been developing the radiation-hardening hard sill technology since the company's inception in 2004. The technology has been proven in many CMOS products and flown in space, both from VORAGO and partners that have licensed the use of the technology from VORAGO. Because hard sill allows hardening of CMOS, rad-hard performance can be achieved very cost effectively. As well as licensing hard sill technology to other leading semiconductor suppliers, VORAGO has developed a portfolio of hardened SRAM and microcontroller products that are available today. So what are the options for selecting components for CubeSats? Commercial off-the-shelf or COTS components have been used. A basic COTS part is unlikely to have been tested in radiation, and it certainly will not have been designed to operate in a radiation environment. There are lots of choices, including all the latest and greatest ICs that have a lot of horsepower and are inexpensive. The only problem is that they're risky. They're risky because they're operating out of spec. The supplier who designed the parts would not recommend that you use these products. One way of dealing with the risk is to upscreen them. If you've done some testing to get a feeling of confidence that the devices will operate in radiation, you are reducing the risk. I think of upscreening as paying for an insurance policy to offload the risk. Like an insurance policy, upscreening can be expensive, and the more risk that you want to offload, the more expensive it gets. It is generally considered that good practice involves understanding the radiation environment that the SmallSat will be exposed to, and understanding the expected performance of the COTS device through an appropriate level of upscreening. There doesn't need to be guesswork involved. It is about calculating the exposure to risk and deciding of how much of a budget you are willing to allocate to reducing that risk. Rather than use COTS with upscreening, you could use a component that was created to be rad-hard. There are a limited pool of options here. They tend to be pretty old, not state-of-the-art, and they are typically very expensive. On the plus side, these are parts that were designed to work in space, so you're not taking the sort of risks that you would with COTS or even upscreened parts. VORAGO products are rad-hard. They were designed to operate in space and have been tested and qualified fully for operating in radiation environments. Because VORAGO's hardening approach uses standard CMOS processing and can benefit from the low cost of CMOS, VORAGO rad-hard products are typically lower priced than the cost of upscreening COTS. You get parts that were designed to be operated in a radiation environment and were tested under the beam without incurring the risk of using outlier parts that have been upscreened. Hard sill technology was developed to prevent latch-up. This side view of a CMOS device illustrates a pair of complementary transistors, an NMOS device in the P-well and a PMOS device in the N-well. There is an unwanted byproduct of the CMOS wafer process that results in the formation of millions of parasitic bipolar transistors that reside in the CMOS wafer under the active CMOS transistors. The structure of the parasitic bipolars looks and behaves like a thyristor if it's triggered, resulting in a short circuit from VDD to VSS. This condition is known as latch-up. Normally, if the device is operated within a reasonable temperature range or is not exposed to radiation or transient noise, these parasitics will not be a problem. However, devices that are used in space will be exposed to ionizing particle strikes, and the resulting charge in the substrate can trigger latch-up. When a particle strike occurs, high energy radiation creates many electron-hole pairs in semiconductor structures. These electron-hole pairs create disruptive currents that can create current and voltage spikes. These currents can cause the parasitic bipolar devices to become forward biased and switch on. This creates a path from VDD to VSS, and the device will immediately start conducting current. A hard reset of the chip can be implemented to recover from latch-up, but it is not always successful, and the chip can be destroyed by the latch-up occurrence. One of the features of VORAGO's hard cell technology is to implant a vertical and horizontal buried guard ring in the substrate. Hard cell provides a highly conductive path that protects the critical circuitry from these unwanted currents. Hard cell increases electron-hole pair recombination to quickly eliminate excess charge. Hard cell reduces the RP well resistance so that the parasitic NPN bipolar device cannot switch on. The base voltage is not able to rise high enough to forward bias the parasitic transistor. The gain of the parasitic NPN transistor is lowered so that the combined gain of the parasitic structure does not approach unity. Only if the combined gain exceeds unity will the structure be able to sustain latch-up. There is another failure mechanism that we need to consider when operating CMOS semiconductor devices in space. Total ionizing dose is the accumulated buildup of charge due to ionizing radiation that will cause transistors to fail after the accumulated dose reaches a certain level. This will cause failure in many CMOS devices starting at only a few K rad psi. VORAGO products are specified to operate at up to 300K rad psi. That means they will survive typically 100 times longer in space. TID causes electron-hole pairs to occur everywhere. Most of these recombine. However, it is difficult for electron-hole pairs to recombine in oxide. Because of the biasing in this region, the electrons leave the oxide, causing a build-up in positive charge in the oxide regions. This positive charge attracts a negative charge at the boundary, which creates a path for current. This in turn reduces the threshold voltage of the NMOS transistor. The first sign of trouble is an increased leakage current. This will continue to increase and consume more and more current until the transistor fails. TID typically is not an issue for the PMOS transistor, as a positive charge in the oxide will increase the threshold voltage. We also need to consider single event upsets. SEUs occur due to high energy particle strikes that can cause a change of state in a chip. Sometimes an SEU that affects digital logic is known as a single event transient. If it causes an interrupt to occur, it can be referred to as a single event functional interrupt. The memory of the VORAGO microcontroller is protected with an error detection and correction subsystem. This will detect up to 2-bit faults and correct 1 per byte as a word is fetched by the CPU. A scrub engine is also used in the background to sequentially step through memory and correct flipped bits. This prevents the accumulation of errors to reduce the probability of an uncorrectable error, which would occur if there were 2 or more errors within a single byte. The speed of the scrub operation can be controlled so that it is possible to trade off scrub speed with power consumption if a higher instance of bit flip corrections are being observed. The memory is laid out so that logically adjacent bits are not physically located in proximity. This further reduces the probability of uncorrectable bits. With the EDAC enabled, the soft error rate is 1e to the minus 15 errors per bit day under conditions of geosynchronous solar min with 100 mils of aluminum shielding. For SEUs that can affect logic, all internal registers use dice latches and triple modular redundancy. A dice latch is a dual interlocked cell structure that uses 3 voting cells rather than a single latch. VORAGO have a long history of radiation testing multiple CMOS products, including both SRAMs and MCUs. The VA10820 microcontroller radiation testing is performed at various locations to confirm that the specification is validated. The TID spec is 300K rad psi. SER with EDAC enabled is 1e to the minus 15 errors per bit day, and LET is 110 MeV. These locations are comprised of Triumph, the Tri-University Mason facility in Vancouver, UMass Lowell, and the cyclotron at Lawrence Berkeley National Lab. The VA10820 is the newest ARM Cortex M0 based microcontroller from VORAGO that was launched in 2016. It is already proving popular in many new CubeSat designs. The device is a 50 MHz microcontroller with a full suite of on-chip peripherals, including multiple serial communications ports, timers, GPIO, and extremely low power consumption. The device comes in 128-pin QFP packages or can be shipped as die. The VA10820 is designed using a radiation mitigating architecture that consists of hard cell processing for latch-up immunity, TID performance up to 300K rad-Psi, error detection and correction subsystem, scrub engine, dice latches, and triple modular redundancy. Radiation performance is rock solid. The VA10820 is used in many new CubeSat designs. The objective of VORAGO is to provide components for any CubeSat budget. There are two particular use cases that are often seen. The first use case is as a standalone onboard controller. In many cases, the 50 MHz performance and low power consumption is ideal to provide a rad-hard central control system for a small satellite. VORAGO has developed a CubeSat controller board and have written up a tech brief that includes schematic and bill of materials that is available on the VORAGO Technologies website. It includes a PC104 interface so that it can be used easily with other standard CubeSat components. Another common use case is to use the VA10820 as a system monitor or watchdog along with another processing device such as an FPGA. The picture on the right hand side shows a VA10820 that is used to configure, load and monitor a Vertex 5 FPGA. The idea is to use the affordable VA10820 as the rad-hard anchor in the system that can monitor and reset any other components or subsystems that may latch up. Part of the appeal of using an ARM Cortex based microcontroller is that it is inherently low power consumption. This is important in CubeSats that rely on solar power to top up batteries. These charts show power consumption curves at different frequencies and across temperature. Different levels of activity are shown in the charts. The high level of activity corresponds to the CPU running full speed and executing complex math instruction, all serial comms clocking at full speed, and all 24 timers with their associated 32-bit counters running at full speed. The chart on the right hand side shows power consumption curves up to 80 MHz. The exponential leakage component is not appreciable below 125 degrees centigrade. There are lots of techniques to optimize power consumption on the VORAGO microcontroller. These include clock gating unused peripherals, taking advantage of the wait for interrupt instruction, and carefully terminating GPIO pins. These techniques are all articulated in a VORAGO application note on power optimization. VORAGO offer a development kit that retails for just over $500. It is easy to use and is supported by different options of software development kits from ARM, IAR, iSystem, and there is also support from FreeRTOS, real-time operating system. A board support package with example projects is available to download from the VORAGO website. One of the biggest benefits of using the ARM Cortex CPU on the VA10820 is the strong development ecosystem. This is a VORAGO microcontroller roadmap. The blocks shown in green are already available. We are working on our next generation MCU that will use an ARM Cortex M4 CPU for higher processing bandwidth and will greatly enhance the set of on-chip peripherals. ARM are a strong strategic partner to VORAGO, and we expect to fill out our portfolio in time with further products based on ARM cores. In summary, VORAGO Technologies has developed a cost-effective way to harden CMOS components. This is known as hard cell technology. It's probably lower cost to use VORAGO rad-hard devices than to pay for upscreening of COTS. The VA10820 is a perfect rad-hard anchor for a CubeSat, either as a standalone onboard controller or as a system monitor watchdog. There is a best-in-class development ecosystem available for the MCU. Developing with the ARM core is relatively easy. The ARM Cortex M0 is optimized for low power consumption. Stay connected with VORAGO to keep informed about the availability of the next generation M4 based MCU. At the beginning of this presentation, I suggested that there was a perception that rad-hard components are too expensive to be used in CubeSats. The new reality is that many developers of CubeSats have decided that they can't afford not to have a VORAGO Technologies rad-hard MCU in the system. The incremental cost of adding rad-hard functionality is somewhat trivial when weighed against the risk of commercial parts succumbing to radiation effects in space and the overall cost of the CubeSat budget.